Nehalem first implementation, you see the first die on the right. It's a monolithic 4-core product. It has each core, we'll go through it a little bit more detail, has its own local cache, but there's also a shared third level cache. We're integrating the memory controller, we're integrating QuickPath. It's all based on our core microarchitecture that I told you about earlier. 4-issue machine. Our competition's best machine is a 3-issue machine, and we've enhanced it with a number of different features, not the least of which is two-way SMT. So this is an 8-thread processor. Integrated memory controller makes sure we can feed the processor. QuickPath means we can get all the I/O and coherence traffic, and then we made sure that this thing has the best power management we can do, because over time it'll go across our product line. Server, desktop, mobile, etc. It has an instruction set extension, SSE 4.2, kind of one step further of what we had in Penryn and 45 nanometer. And we're clarifying our production date is Q4 2008 for us to be shipping Nehalem in production.
That's the first time that the Itanium and the Xeon line is going to
are on the same infrastructure. Yes, they can share infrastructure.
So what does it mean for OEMs?
What that means is an OEM who's building a very large system can invest one time in terms of system infrastructure for node controllers, I/O, etc., all built around QuickPath. And they can have different system offerings where some of the systems may be Itanium and some of them may be Xeon. I'm not sure that we have sockets that are the same socket. But if you look at where an OEM makes a significant investment, if they're building a very large system with a large number of processors, they need some custom node controllers that have all the logic to share memory across large MP systems, and they need I/O controllers and that sort of thing. So they can share that same common infrastructure. Even if they need to have two physically different boards, it can use the same chips on the boards. This is the concept of Nehalem as a scalable design. The first implementation we showed you was a 4-core design. This shows the fact that it's made out of some building blocks that we can recombine. So we can compose different versions of Nehalem based on the different pieces that we have here. The IA core, the cache module, the QuickPath module, the memory controller module, and the integrated graphics. And this shows two examples, the one that we showed you physically, the 4-core design, and then this shows the fact that we're going to, for the MP segment, have an 8-core design with additional memory bandwidth and additional QuickPath connections to support the machine. The microarchitecture enhancements, again, based on the core microarchitecture, so it's that 4-issue machine, captures all those learnings, makes them better in the following ways. Increased parallelism, this 33% more micro-ops in flight. What that means is that we have some hardware, some logic, that can deal with the out-of-order nature of the machine. On core, that was 96 micro-ops in flight. This one is 128 micro-ops in flight, so that we can capture possible executable code across a wider window. And that's good in general, but it also is important in that we're adding SMT so that we have two possible threads that we can execute on using those resources. The other thing is where you care about performance, such as media, there are certain places where you get slowed down by unaligned accesses, where you're going to find a byte here or a byte there. This machine has better access to those unaligned cache accesses and helps you go through those media or pixel-based applications faster, sorting through memory. And for things like MP, where you're trying to have coherent structures that are in software, you need a concept of a locked operation where you grab a certain database element in a locked fashion, write it, and then give it back. We've made sure that there are some operations, some opcodes in the x86 that allow you to do that. We've made sure they execute better on Nehalem. So media kind of applications, database kind of applications, both can be sped up here. And then branch predictions improved by having a 2-level branch predictor this time instead of a single level. So some pretty interesting improvements, refining this core microarchitecture to have a better engine going forward. A little bit about SMT, 2 threads simultaneously in each core. Fundamental reason for doing that is it's the most power efficient performance that one can get when the workload is inherently threadable. Servers for sure, many of the media applications in Workstation really benefit from simultaneous multi-threading. And its benefit is higher than it used to be because we have larger caches and because we have more resources for execution in flight, and because we have more bandwidth, we can get more benefit out of it. Why did it go away? It's a very practical perspective that there's only so much change we could tackle in the core microarchitecture, the core 2. And that was one level of complexity we felt we couldn't get into the design and the schedule. So it's fundamentally a concept we believe in, and at each generation we have to make an implementation choice. And we have to prioritize the benefits. You saw that even without SMT, we got a 40% benefit and a 40% reduction in power when we went from net burst to core. So we prioritize getting that benefit in the most timely way. This is the cache hierarchy. The interesting thing here is that we're going from a 2-level cache in Penryn to a 3-level cache here. Still have the 32K for code and data. Those are the very small, very high-speed caches. We still have an 8 meg shared cache, but here we've isolated the cores from each other by having an intermediate 256K cache, which is, I'll call it fairly high performance and allows each of these to execute independent of the other cores out of the shared cache. Okay, so it isolates them from each other. The other thing that's interesting is it's an inclusive cache policy, meaning if there's data cached here, that's also reflected here and also reflected in the last level. The reason that that's cool is that if this core needs some data, it pulls the last level cache, finds the data's not there and has to go out to snoop to memory, you automatically know that that data is not here, not here, and not here because of the inclusive policy. You don't have to go interrupt these to snoop them. It also means that you can have a very effective system level snoop, that a system can request a snoop to the last level cache and know if certain data has been modified anywhere in this subsystem. So it's a very interesting approach for keeping high performance and also keeping the energy efficiency. You don't have to snoop as often. These are the systems, system connections that we show here. First generation Nehalem is configured with 2 quick path interconnects, 3 memory channels, and connects to this Tylersburg I/O hub, which is really optimized, the design point for DP server and workstation, but also can be configured with a single link as a single processor desktop configuration. So we'll expect the initial Nehalem to be used for both DP systems in server and workstation, and also the UP desktop. So 2 links are possible per processor. Each link is up to 25 gigabytes per second total bandwidth, which is higher than other point-to-point, coherent architectures. So pretty good step forward here in performance. If you look at the memory controller, up to 3 channels per socket, supported by the processor, up to 3 DIMMs per channel. And we're supporting DDR3, and we have both registered and unbuffered memory that can fit into those channels. So you have to choose whether you want a registered memory or unbuffered. Typically the desktop folks are excited about unbuffered, it's the cheapest. You could also choose unbuffered ECC, or you could choose registered if you're building a server. With the choice that we've made, looking at a 2-socket system, you have a specific example here of DDR1333 comparing to Nehalem dual socket to the best platform we're shipping today, which is the one we launched in 4th quarter, the Harpertown Stokely, the thing that's today used in, say, an Apple Mac or the highest end workstations. We're going 4x in bandwidth when we get to Nehalem.